Hello and welcome to another video. In this video we're going to be continuing the on-site interview loops, and we can do the meta one today. So we're going to focus on clean code and making sure I don't make some dumb mistakes and things like that. And going to do some dry runs and not just like run and rely on that. So let's see how this goes. Okay. Alright. Can do strings return array of all the start indices of P's, anagrams, and S. Okay. So 0 is here, and 4, 5, 6 is here. Wait, 1, 2, 3, 4, 5, 6 here. Okay. All right. So I think there's like a cleaner way of doing it, but this should be good enough. We can essentially maintain a count of letters and just make sure the count's the same, and we just sliding window it. So what would happen is like we'd have a window like this with this, and we just check like is the counts the same. Yeah, so let's go with that. And you can optimize it a little bit because comparing counts is of 26, that's fine. Alright, let's go P len P, S len S. Okay. So, yeah. Yes. Okay. So we're gonna go S count. SR. Okay, and if right is, so we need to like move the window. So if right is greater than or equal to length P, then we gotta go S count SL minus, and if S count SL equals 0, we delete it. Alright. And then just if, yeah. And then we'll increment the left. We can also not use a left, I guess, but these small things don't really matter. Like technically we only need a left. We don't need a left, but it doesn't really matter. Okay, so if S count equals P count, then we'll just go result and left. Alright, let's dry run this guy. So P count here will be A1, B1, C1. S count will be nothing. And left will be 0. Right will be 0. Okay, let's go. So first we're going to get C of a count of 1. And this is not too big. So then we'll get B of a count of 1. Good. A with a count of 1. Now these are equal. So right is still not greater than this P. So that's fine. So here we're going to put in left into the result. Okay. And this is right. This right was 2. Okay, now at right equals 3, we're going to add an E. And we are going to subtract whatever was at the left. So this guy, now left is 1. These are not the same. Keep going. 4, add a B, subtract a B, so it stays the same. Not the same. This is this. 5, add an A, subtract an A, not the same. 6, add a B. Is that right? Yeah. Wait. 1, 2, 3, 4, 5, 6. Yeah, so 6, add a B, subtract whatever was at 3, so E. All right. Move it up. So this is actually here and 6. Okay, 7, add an A, subtract a B. All right, not the same. 8, add a C, subtract an A. This is the same, so this is 8, 6 now. And this is 1, so here we just put in 6. And then we just basically keep going and we don't have any more, so yeah. All right, looks good to me. Let's see, how many dumb errors today? All right, nice. Given the root, return the lowest common ancestor of the deepest leaves. Okay. Deepest. Okay. All right, so here. So first we have to figure out what the deepest leaves are. So once again, I'm not going to do some weird like one pass. I'm just going to keep it simple. And then if we do need to optimize, we can do that. But first step, traverse, find the deepest level. Second step, figure out, are all these, okay, these nodes are all unique. So we can do this one of two ways. We can either find the deepest level. In this case, it would be, let's say, like 3. And then every node that's on the deepest level, we can do another traversal. Every node that's on the deepest level will return 1. And then whenever we get an ancestor, that its total will be like the total we get to it, the left and the right total, and the node total, I guess, ends up being the deepest level, then that's the ancestor. So in this case, this will return 1, this will return 1. We're looking for a 2 because there's 2. We'll get it up here. This will be the answer. One way, or we can alternatively take all the nodes at the deepest level and put them into a set, and then that's how we know we're at the deepest level. So either find the level or put them into a set. I guess level is more optimal, so we'll go with that. And then yes, this is basically just like lowest common ancestor, except now we need multiple nodes. So, okay, sure. So we're gonna, yeah, first deepest level. Now, actually, if we don't store the nodes, how do we know how many we have? We can do that with variables, yeah. Okay, so we'll go deepest level equals 0. Can the root be null? And nodes at deepest level is going to be 0. All right, so we'll just go count nodes at deepest level or whatever we want to call this. Or just call it whatever, traverse deepest or something. Okay. So take a node, and we're going to give it a level. Okay. So if level is greater than deepest level, so we can just pass these down. Or you can make like an array or something, whatever. So if not node, return. All right. So if level is greater than deepest level, then deepest level equals level, and nodes at deepest level equals 1. Well, if level equals, alternatively, let's just go with this, then we don't need an elif. Nodes at level deepest level. Okay, then if they're the same, then we want to increment. Okay, then we want to traverse left and right, and yeah, so traverse deepest. Node left level plus 1. Same thing for the right. Okay. All right, and we call this on the root. Okay. That will give us the number of nodes we're looking for. Now we run this again with a similar, except now we want to find the root. So result equals 1. Okay, well, and then we'll call this find LCA. Okay, that no return. Don't need that anymore. So if level is equal to the deepest level, we need a total here. So total. Okay. Then we're going to go left equals yeah, so left equals find LCA. Left. So here we can also return a 0. And level plus 1. Right, so if all of this together adds up to nodes at deepest level, then this is our answer. And if this is our answer, we don't want to keep propagating, so we just want to return like 0 or something. So go non-local nodes at deepest level. If left plus right plus total equals that, this is our answer. And we can just return 0. Otherwise, return all of it. I mean, technically, yeah, this is fine. Technically, we probably never need to add the total because this is children. So it shouldn't matter. Like, if level is deepest level. Yeah, like the only way this happens is if it has no children. But this could be the node at the deepest level. Can the node at the deepest level be an ancestor of itself? That's actually a good question. Okay, so yeah, so if the deepest level is the root and there's nothing deeper, then that's what we return. Interesting. Yeah, DCA of one leaf is itself. Wait. So 0, 1, 3, null 2. What does that look like, actually? Yeah, I guess before. Yeah, so we'll just return this. I think this is fine. And then we can return. So I guess we can say here, if deepest level equals 0, then basically just return root, right? If there's nothing else. Okay. Yeah, but let's walk through most of this. So here, essentially, like, let's walk through this one. So here, these two will be at the deepest level. So this node's deepest level will be 2. Deepest level will be 3. Now this is gonna have 2. And then this will be our answer, and then we'll return 0 and we're good. This is gonna be this case. Let's walk through number 3. Get some more space here. So we have node 0. And it goes over here and over here. So 0 goes to 1, 3. I guess like this. Null 2. I guess this is what they want. Deep cells 2. LCA of one node is itself. I see. Will that be the case in my code? Yes, it will be. Yeah, no, that makes sense, yeah. So if there's multiple nodes, then you have a parent, but in this case, this will, yeah, I think so. This will work in my code because this left plus right plus, so you do need this node value. This left plus right plus node value will be 1, and then we'll get everything correct. So actually, I believe for the root, we don't actually need this case because if it is the root, we're going to get it, and we should be fine. Let's give it a whirl. And we just call CA on the root, level 0. We traverse to root 0. And let's do a quick final check since we have a lot of time to make sure we're good. Deep level. Okay. Yeah, maybe some stuff with the non-local. You can easily turn this into like an array and then you don't need these non-locals. But yeah. So flow level is deepest level. Okay. Seems good. Total is 0. Okay. I mean, we probably just want to do like a total just to make this cleaner, right? So if total, otherwise return total. All right, I'll say root 0. Let's go. Ooh. Oh, we're not returning. Yeah, I'm gonna be pretty happy as long as we don't get an actual implementation bug. If it's some small stuff, who cares? All right, is that it? Yeah, okay. Nice. Okay. Given array nums, partition 2 subsets, subset is equal. Subsets. Okay. And the constraints are okay size, okay. All right, so the sums are equal. So, I mean, some obvious stuff is like, wait, is it 2? 2. Okay, so first we can just get like a total, right? So just some obvious stuff here. And then we can say like if total mod 2 it does not equals, yeah, total has to be divisible by 2. Yes, because we have to partition to 2. So not equals 0, return false right away. Now we have a half equals total mod 2. So that's what we can start with. So essentially get a sum divided by 2, that's what you need for a half. Okay. Now I think what we need to do is we can basically figure out, like, can we make one partition? So for example, if we have 1, 5, 11, 5. So this is 22. So essentially we need to build a subset with a sum of 11. So it's like, can we just take some random numbers here, get a sum of 11? And this is just a take or not take or knapsack or whatever DP. Now can we fit this with a constraint? So this will be like n times the total, which will be like sum of n. Yes. So that'll be like 200 times 100 is the sum of n times 200. Kind of pushing it, but I think we're good there. Yeah. Can we do some optimizations? Like, yes. So we can sort the array initially, and then like if the number's too big, then we know everything else will be too big. Yeah, I mean that'll help. It's just like a runtime optimization, won't really matter, but every little bit, I guess, because the sort's going to be free because it's going to be like an n times times this guy. Okay. So now we just do a basic DP. We'll go top down, easier. All right, so we're going to go index and total. All right, so if index equals length nums, then total has to be 0, like we had to have gotten it. If total equals 0, return true. Otherwise, return false. All right, so that's our base case. Now we basically take our do or take or not take. So if nums I is too big, we can just return immediately because we can't take anything else. Otherwise, we go return dp of I plus 1 total minus nums I, where we take the number, or dp of I plus 1 total, where we don't take the number. And that should be 0, and then we put in the half. I mean, we can definitely do a dry run here real quick because we have so much time. Yeah, I think it's more like a medium, definitely not a hard, so I guess just luck or whatever. All right, so like what do we get dp of? So half here is 11, so what's dp of 11? So dp of 11 at index 1, I guess. What is that going to be? So yeah, you can probably do more optimizations where you could figure out like what's the sum left and if I don't have enough, but those are all small things that will they will improve runtime, but not, won't improve big O. But anyway, so yeah, so here essentially we're saying, do we take the 1 or not? So our cases is dp, so I guess actually this is the index. So if we take the 1, then our total is 10, or 11. So what's dp of 110 now? So we can take the 5 or not, so that's going to be dp of 2, 5, or dp of 2, 10. Okay, and what's dp of 111? So we can take the 5 or not again here. So dp of 2, 6, dp 2, 11. All right, it's dp of 2, 5. So that's going to be dp of 3, 0. So we'll just return this as true to save time. We don't need to recurse anymore because 3, 0 will be true. Okay. What about dp of 2, 6? So that's going to be dp of 3, 1, which is false because, yeah, obviously. And 3, 6. I mean, we'll just say it's false because there's no way. So this will just be false. Okay. dp of 2, 10 is going to be dp of 2, 10. Yeah, so this will just be false. We'll just do this faster. There's no way you can have a solution there. Okay, dp of 2, 11. Yes. Okay, so there, that will be dp of 3, 6. Yeah, this will be false for sure. And the other one will be dp of 3, 11. And dp of 3, 11 will obviously be true because that is just the exact number. So we'll just say this is true. Speed things up. Okay, so now we'll replace, so this is true. So this is true. 111, so this is true. Okay, so there we go. So we have true. All right, let's do a quick dry run of the other one just because we have so much time. All right, so here we have 8 and 10 and 11. Oh, so this can't be split into 2, so we'll just return false. Okay, it looks good. All right, let's go for it. Cool. Yeah, so definitely could have done this like 5 minutes faster, but whatever. And yeah, so it's actually kind of funny. This one and the Uber one I did a while ago are like the easiest two so far. Every other one I think had a hard, so kind of interesting. But it is what it is, randomness, so whatever. But the hards weren't that bad. Like, they were all doable. So let's see if we get a... And I'm definitely a lot happier with this one. Didn't make any dumb mistakes. I think we had some small syntax things, which is whatever, but I didn't have any like glaring edge cases that I missed or anything like that. So okay, so that wasn't too bad. Yeah, could have done it in 20 minutes, but I mean 3 mediums that were, let's see, this is a fair medium. I'd say it's a medium for sure, medium for sure, medium for sure. So yeah, 3 mediums, and yeah, without the dry run stuff, could have done in 20 or 50, whatever, 15 if it was like some competitive programming thing, probably like 15 if I would have just like done things as fast as possible, maybe even less. But yeah, overall pretty good. 24 minutes, 3 questions. Okay, so yeah, I'm gonna probably do some more of these in the future. So I think so we still have 1, 2, 3, 4 left. Hopefully get some more hards, and then hopefully keep up this just paying more attention to the problem this time, not rushing it, doing a dry run, kind of more realistic scenario. Like, it's like the interviewing versus competitive programming, like contest type thing. If you're doing contests, you just want to blaze through it, no dry run, whatever, just fast as you can. But for these interview ones, you definitely want to like pay more attention to your code and make sure you're like writing it well, variables are good and all that. So gonna do that format. But yeah, thanks for watching.